to James. So I realize you've all been listening to talks for a little while now, so I'd encourage everyone to sit up in your chairs a little bit, because I'm going to start things off with a bit of a story, and I don't want it to be a bedtime story. So I'd like you to cast your minds to 15th century Portugal. Pepper is one of the most valuable resources at the moment. You are all noble people of Portugal, and you want pepper on your dinner table. And voyages have been set off, have been sent in ships around the coast of Africa, but a lot of them aren't returning. And you want to make sure that they are going to return, so you ask for some map makers. And these map makers are going to come along, and they're going to make sure that your ships get to where they need to go and get back with the cargo that you expect them to. So in the present day, this is analogous to the moon. Currently, it costs $25,000 to take a gallon of water into space. It would be a lot better if we could get that from the surface of the moon. So, continuing with that analogy, I'd like to introduce our crew. We have our esteemed map maker, Dietmar Bacchus, our intrepid navigator, Eleni, our science officer, Tony Dobrovolskis, and myself, the technical officer, Timothy Seabrook. And I'll pass you on to our navigator, Eleni, now.
So why water? Why is water the most important resource on the moon? Broken down into its constituent parts, water has many applications. It can be used to make rocket fuel, and of course also be used for keeping astronauts alive. Now, the moon as a whole is a very dry body. However, there are certain locations where there are reservoirs of water, and these locations are at the north and south poles. So we know that craters are everywhere on the moon. However, at the poles, the floors of these craters will often never see sunlight. These we call permanently shadowed regions, or PSRs. Temperatures at these are very, very cold places, and temperatures can drop to below 40 degrees Kelvin. And this is why water can be thermally stable in these places. And here's what permanently shadowed regions look like. So in this map here, the blue areas and the craters are showing these permanently shadowed regions. We know from remote sensing studies that there is water here. We have neutron spectroscopy showed that there is hydrogen in these areas, and then later on the LCROSS mission revealed they did an impact into one of these permanently shadowed regions. It's complete darkness, and the plume that was ejected was shown to have 4.6% weight percent water. So we now have a first order approximation that there could be quite a lot of water in the moon, but we want to know exactly how much, and we want to know the true extent of where this is if we're going to have resource prospecting missions. We need in situ measurements. How do we do that? That means landers and rovers. And to talk more about that, I pass on to Dietmar.
Thank you, Lenny. Well, let's have a look at that. Indeed. Yeah, it's not going anywhere. Where do I point to? Well, I guess you have to stop the movie. Okay, that's too many. Well, indeed, there's about it's half a dozen missions at the moment in preparation to go to the moon, 2 polar regions. And it's quite interesting to see that not only NASA is investing in that, but also other nations and especially the private sector. So what do these people need? To cut a very long story very short, well, they're lacking mapping data. Mapping data doesn't seem to be adequate. And that's quite interesting. We're collecting data since a long time on the moon. So let's have a quick look at that little rover there. What happened if it goes the wrong direction? It took us hundreds of millions to get it there. Now, the mission could be over in a couple of minutes if it goes the wrong direction into the crater instead of in its suitable path. So let's go forward. Oh, voila. So, too many again. So, mapping on the moon. Reconnaissance is done since the 1960s. Some of the early missions started as early as the late 50s. The Russians got there first with the Lunar 9 mission, getting the backside of the moon. We have a plethora of data, wealth of information has been collected during the centuries. And since 2009, the Lunar Reconnaissance Orbiter has actually changed things quite dramatically, collecting lots of information, topographic mapping data, which is useful for mission planning, especially on the poles, we thought. Let's have a look at this data. So there are two sensors on board, which are incredibly useful, especially the Lunar. The Lunar instrument is a laser altimeter, which creates digital elevation models. What you see on the left side, actually, brilliant topographic information. You can actually see the whole planet, it's a reference for the whole planet. But there are artifacts on that. You see those striping effects. And these hamper any kind of meaningful mission planning for lunar reconnaissance missions. So on the right side, you see optical images collected by the narrow angle camera. And there's two on board, which do 2.5 kilometer strips each. And you try to map them together. In time, you should have a nice picture of the moon. However, there are shadows and other features, and they don't fit quite well together in its georeference. So you have this kind of ugly mosaics you see on the top right. But then if you zoom in, then you see a lot of detail on that, which we really need, with 0.5 meter resolution. And it shows all the small craters, which also eats up a rover very easily. So next one. So if we overlay those two data sources, we're seeing a very smooth 3D rendering on top right. This is great, fantastic, but let's zoom in. So on the left side, you see that zoom where you have the LoLa, digital topographic data, very big artifacts, 20 meter resolution, and a very high resolution. It's a bit dark, but that can be fixed. Optical images. And that optical image doesn't quite fit on the top of that digital elevation model. So there's a correlation issue. That's zooming in a bit further and take a very nice region, for example, that crater. That crater, we expected to have a nice shape. You look at the bottom right and you actually see, you see that little hill here. We didn't expect it to be there. Now, judging the quality of the data, we can't really say, is this true data or is it false data? The quality of the data doesn't really help us with that. So we have to fix the things before we go forwards. So let's sum up the problem. Water is in the polar regions. To get the polar regions is very, very difficult. Now how are we going to do this? Well, we have to have landing missions, and for that we have proper mapping data. So we have to fix the mapping data first. It's good news, we can do that manual, but it will be very, very hard and laborious. So how's that been done normally? This is a quite nice picture, shows software from USGS, this is the ISIS, the Integrated System for Imagery and Spectroscopy. Do not confuse this term. And you see actually a photogrammetric system. All what you do here is collecting features between different data layers. You find out different reference and you correlate those data layers and you produce high quality maps. It takes the experienced user weeks and months to do great data sets suitable for those missions we ought to plan. So what's interesting on that? Well, we're looking for manual feature extraction. And looking at the planetary body of the moon, we'll see that, well, there are craters. Craters are everywhere. Craters in the elevation data, craters in the pictures. Well, and there are also in other planetary bodies. So craters is the feature we want to collect to correlate those images, improve the maps, and guide the process of mission planning. Now this is a bit crazy. There are about 80 teams worldwide looking at algorithms to do this manually. On the whole, that works on certain region, not in others. It works on certain data set, not in others. So that's quite a little bit daunting. But more intriguing, the community hasn't picked up all those algorithms produced from time to time or on a very short basis. Almost every project still works on manual labor. That's quite daunting. Isn't that a bit crazy to do that by hand? Why not to use artificial intelligence to create algorithms, to create procedures, to do this automatically? And Tim tells you what we've done in the last couple of weeks.
Thank you. So what Dietmar identified was that there have been algorithms put to this problem before, but a lot of them are catered only to the equatorial region, and more than that, most of them haven't been adopted, or rather all of them haven't been adopted. This is often because the code is kept behind closed doors, or the data set is kept behind closed doors, and it isn't shared with the rest of the community. So what we've been trying to do is create an open source solution using equatorial and polar data. that can be used by the scientific community and by the mission planning community to really set the stage for the future of lunar resource missions and other missions thereafter. So, to highlight the problem that's being faced at the moment, I know Eleni went through this, of being a planetary science grad student and being asked to go through lots of pictures and say, where are the craters? Can you draw boxes around them for us? And we had to start in the same place. We had to go through, we went through 40,000 tiles of the moon and went through and decided whether or not there was a crater in the image or whether or not there was no crater in the image. And as you can see from this, it's not always easy. On the right-hand side, there's an odd shadow. That could be a crater, could not be. So we had to prune out these examples so that we gave good lessons to our deep learning network. So this summarizes that, the collection of 40,000 tiles, which is basically taking our algorithm to school. It takes our artificial intelligence and feeds it a lot of information about what makes a crater, what isn't a crater. And this data set will be invaluable to future teams who will be approaching the same problem and forms the basis for us to be able to match together the elevation model and the optical images so that we can remove those artifacts and so traverse planning can be made. So this is the form of the artificial intelligence. It's a deep learning classifier. It follows a fairly rudimentary approach, which is the LeNet. But it was incredibly effective. So it takes several layers of convolution with dropout, a lot of details that most of you probably don't need to know too much about. But it follows this idea. So this is the conventional approach. This is a convolution filter so this isn't a crater. This is a mathematical model that was developed by Casey Handler, thankfully. And so we take a shape that looks like a crater and we adapt it and change it and run it over an image. And when the image matches the shape that's in this filter, then it returns a positive result. And this allows the algorithm to find craters. This goes through many thousands of adaptations with the shadow moving around with the orientation and the foreshadowing. And that takes a long time, although it does reduce the need for a human. This is a more conventional approach that's been used in the past. It's very good for equatorial regions, but you can see in the background of the image that it's very uniform. This means that when there's a lot of other elements in the image, then it doesn't work very well. So for polar regions, where there's lots of shadows, where the whole crater is filled with a shadow, it doesn't work so well. And I think it's important for understanding to show that the deep learning classifier is based on exactly the same idea. But rather than just having one shape of a crater, it gets fed tens of thousands of images that we hand-labeled, and that allows for a very abstract set of ideas of what craters could look like, with the edges eroded, with partial occlusion, and using exactly the same passing over an image allows those craters to be identified and extracted. And we achieved this using Intel Nirvana, and that allowed us to quickly iterate through different structures of deep learning network and really get to performing good results very, very rapidly. So I'll pass over to our science officer, Tony, to tell you a little bit about the results.
So, using the convolutional neural net that we've done, we were able to obtain an agreement with human judgment 98% of the time, which corresponds to what we call an error rate of only 2%. Now, in comparison, some of the prominent recent groups have achieved comparable error rates of more like a dozen%. So this represents an improvement of 5 or 6-fold for our method. Furthermore, the key to this is our polar data set. If we train, for example, our crater detector on an equatorial set, which is the first row there, we achieve an error rate of about 5%. If we train our polar crater detector an equatorial set, we get almost a 10% error rate. But if we use polar craters to detect polar craters, we get down to about 2%. In fact, if we use the entire equatorial and polar data set together, we get down below 2%. But the real payoff in all this is the time saved. Here's a comparison. Assuming that a human is essentially perfect at detecting craters, it still takes several hours for a human being to go through, say, 1,000 images, which may or may not have craters in it. For our single-layer convolution, the accuracy is not that great, and it takes much longer, maybe about 10 hours. But with our convolutional neural net, we find an excellent accuracy, but it takes only about a minute to go through all that. Okay. There we go.
So this work really sets the stage for future FDL teams, and I know we're not completely done with this. We've each individually expressed interest in tidying things up and writing the documentation. Sorry, guys. To allow people to continue this. So if you remember the initial problem of dealing with these artifacts at the top, then this crater extraction is going to allow us to overlay images, just as you see there, and compare what's in an optical image compared to the artifacts in the elevation model. So where there is a lack of correlation between an optical image and an elevation model, then we know that what we're looking at isn't really there, so it can be cleaned out of the image, and this will allow for traverse planning to be conducted. Now we've been talking with, I know James mentioned that there's been some interest from commercial partners, and we've spoken to a couple of those, and that's been echoed in the interest of setting up the future for landers, for resource missions on asteroids, and so on. Individually, however, we are personally excited about a few prospects, and I think I'll let each of us introduce what most excites us about the prospect of this work. So, coming from AI and machine learning, my personal passion is for multi-agent systems, for lots of robots working together. And when I came to FDL, I really envisaged this future of teams of robots going over the surface and trying to stay in the sunlight and trying to measure where the water would be and really be a good team on the surface. That's what I would really like to see. Tony, how about yourself?
Well, for a planetologist like myself, what's really exciting is the prospect of improved feature analysis. Like, for example, not just craters, but say boulders, cliffs on the moon or elsewhere. And even restricting ourselves to craters for the moment, you don't want to just know whether there's a crater or not. You want to know its center, its location. You want to know its diameter, its depth, all sorts of things which might enable you, for example, to distinguish its age, whether it's a young crater, an old crater, perhaps ultimately whether a given impact crater was caused by a comet or an asteroid. The implications are awesome to me.
Okay, we got the sign that we have to wrap this up. So for me, it's very easy. I like to make maps. There will not be any autonomous navigation without great maps, so I like to do maps.
I like that response.
So my personal interest is in computer vision for rovers on Mars, and I think autonomous rovers are the future of space exploration. So feature detection in the camera will be really important. So that's it. We would just like to thank very much FDL, Intel, and Space Resources, and to you who raise a glass.
I mean, it's pretty phenomenal. I think that does almost fulfill the definition of magic, so thanks. I know you guys have had a phenomenal ride. You did really great, so well done. And so I'm going to throw it open to our reviewers. Pete, do you want to jump in?
This is really fascinating. One of the questions, and I don't know if you get it or not, but one of the very interesting points on the moon, particularly on the poles, is can you find uncollapsible latitudes? space. Is it relevant to that?
We looked into that a little bit. It was one of our initial motivations, but most of those latitudes so far known are closer to the center of the near side. They're more equatorial. We hope that we will be able ultimately to distinguish collapse features from all those shadows in the polar regions.
I think it would be a question of getting enough training data. For craters, we need tens of thousands, and that's easy because the moon's covered in them. Just, more examples. It might be possible.
Yeah.
Okay.
The image that you showed was really difficult to label. Do you have an estimate of how often humans make mistakes?
So the question was an estimate of how often humans make mistakes.
So we didn't just do a once through when we were labeling these craters. We each had to bet against each other because each of us had different ideas of what looked like a crater. And we started off and we were like, anything that's in the image that looks like a crater, we'll say there's a crater in the image. But that didn't work out so well. And we had to end up refining the data set that we had by triple vetting. So through that process, I would say we cut down at least half of the results of the labels that were given to us at each stage, and really got to the essence of what was a crater or what was not.
One thing that might be possible to build the data set larger would be to make synthetic data, where you have a known high-resolution model and you render a low-resolution image, and then you know what the right answer was, even if it's hard to tell from the low-res version.
That's true.
Yeah, after your question about human judgment, it turns out to be very dependent upon the resolution to which you want to work, the limiting resolution. Also, other considerations such as illumination angle. And so there is some information about this, and we're hoping that our successors, if there are such, will be able to look into that a little deeper.
Great work. I especially commend you putting together a data set to contribute to the greater community. One question I had was, is there an importance in being able to find multiple craters within a single larger chip, which classification model can't do?
And importance for science, or?
Or sort of increasing the ability of your model to handle larger and larger chip sizes?
So one of the extensions of the work would be to include segmentation on a pixel-by-pixel level, so that we can perform not just the co-registration, but to identify those more complex features. At the moment, a set of multiple craters would be identified as a scene containing craters.
Thank you.
Amrish.
Great presentation. I really like the initial Portuguese analogy. It's always fun to talk in analogies, so wonderful job. One of my questions is around Earth observation algorithms. As you may know, there's quite a few companies actually in the area as well, and several tens of millions, if not more, dollars have gone into these companies. And they're developing algorithms that are quite tangential to what you presented today. Namely, they're developing synthetic, I would call artificial targets, just like you showed. And using those artificial targets, they're running them through an AI filter in essence, and feeding it real data to see what pops out. Was there any type of potential collaboration with Earth observation algorithms in what you've done?
Well, we could have done that, but that wasn't really the perspective of the system here. We want to, FDL is a big sandbox. If you take something out of the box, that would probably compromise what FDL tries to do. So, which companies are we speaking about?
There's quite a few. There's Google up until recently, Orbital Insight as well.
Yeah, we are aware of that, what they do, yeah.
Just a very quick follow-up is the chart that you showed that we had both data sets, both equatorial and polar, led to a smaller error rate. Is that due to just more data makes it better, or is it due to polar craters have a distinction between equatorial craters?
I guess it's a mixed bag of things. On the equatorial side, we use a JPL test site, and we have a good number of craters. We could increase that, but we focused on the polar region to have as many samples there as possible. So we got those results we wanted to have in the polar region. Tim might have something to add.
So there were some key differences between the equatorial and polar data. We did, as always with deep learning, if you have more data, then things are going to turn out better. But in general, I wanted to go back to your last point about the mapping. Dietmar expressed some interest in forming these sort of intelligent maps from what we've been doing, and I know he works in geoinformatics and would hope to make his own life, as well as the lives of other mapping companies, easier with techniques like these, and they'll be available to those guys too.
We're confident that with an expanded training set, we can improve our results even more.
Great. Any thoughts from NASA? Yeah, Victoria? Jesse? No pressure if not, because it's break time, and we are on schedule. So big round of applause for everybody. So as mentioned before, we're going to kick off with our Helio teams at 3, so there's a 10-minute break. And if you can please be back here and sharp on the dot, we'll get going in part 2. Thank you.